Hey, welcome back to Fat Mama Physics. In this video, we're going to continue with the Bohr's model, and essentially we are working with his assumption that the electrons are exhibiting circular orbits around a proton, in which we use circular motion to model that. And in this next question, number 2, first, I would like to show us how a de Broglie wavelength plays a part in his assumption that the angular momentum is quantized, and then later on to kind of move us towards where we can combine his classical understanding of these circular orbits with this quantized angular momentum to show that the Bohr's radius can only take on discrete values of this one over here. Okay, so that's essentially what we want to show in this one. Don't worry, this is not just the endpoint. We will eventually use Bohr's radius to find how the energy levels in his for the electrons are also discrete as well. So recall that in the previous video I mentioned how Bohr just found the integer of his angular momentum to be h over 2 pi just out of chance. There was no real, it was just from the data, and from his experiments, that's kind of what was found, but then how to get there wasn't quite shown, or we're not sure why that is. However, when de Broglie came along with his de Broglie's wavelength, we are able to maybe show some connection between the two, or why there is these discrete values of h over 2 pi. So where does the h over 2 pi come from, essentially? These integer multiples of that. So to build a connection between the two, we kind of have to see that these electrons, if they're matter waves orbiting around a proton, they can also be modeled like a standing wave that would take the shape of would fit very nicely inside these orbits as standing waves, so that the number of waves that are able to fit inside that radius, n times the number of wavelengths, is equal to the circumference of that orbit. That is 2 pi r. And the wavelength here is de Broglie's wavelength, in which that is essentially h over mv. In mv is the momentum here. So if we put that inside this relationship, then we're going to get n e times h over mv equals to 2 pi r. Okay, and if we rearrange this one here, let's say we move mv up to the top, then we're going to get n times h, and let's say we divide the 2 pi down over here, then rearranging this is going to give us mvr, in which mvr, hey look, is the angular momentum. And this here is n is the number of wavelengths, or we can talk about as some integer, and then h2 pi here shows up. So if we model the electron as a standing wave in these orbits, then we are able to show that electron behaving like a wave according to de Broglie's hypothesis, and therefore supporting this random value that Bohr just pulled out of his experiments. And ideally, a standing wave with some integer value n should not lose energy, so that in a sense, these electrons, if they behaved as waves, wouldn't necessarily be losing energy as it is orbiting around a nucleus. So it's very interesting how Bohr's model of an atom kind of combines a little bit of classical theory as well as some of this quantum theory as well, quantum mechanics theory. So later on we'll still see that because of this, there are still limitations to his model. So here we go. That is the showing the relationship there, where this h over 2 pi comes from. Next up, what we're going to do is we're going to use this relationship to help us find discrete values of the Bohr's radius. So these questions down here kind of break it down to help you pretty much combine this over here with the total energy of the electrons. So we're going to do this one step at a time. It looks like, so these questions are kind of just prompting you to what step to do here. So essentially, the next thing we want to do is we want to take this guy and we want him to make it look like this, okay? So to do that, it looks like some square values involved, and it might be nice to actually square both sides of that equation. So starting with this, if we square both sides, we're going to get the following. And if we want it to look like this, nv squared, then we have to move the r over and one of the m's over as well. So that's what we're going to do. We're going to divide by 1m and r squared. And which means we're going to be left with mv squared is equal to n to the power of 2, h to the power of 2, 4 pi squared m times the radius squared. Okay, so there we go. So that's the next step. And the reason why we want to do that is because mv squared is going to look something similar to something like kinetic energy, for example. So since mv squared is equal to ke squared over r, which is what we showed before in this relationship from 1b, we can then equate that other side to ek squared over r. Okay, so we can say this is equal to ke squared over r, so that we just get this one over here. So that now what we can do is we can rearrange this to show that the Bohr's radius will take on specific values, because if you take a look at this side, all of these are all constants now. So to rearrange this equation above for r is what we want to do next. We can see how one of these r's are going to cancel out, so we probably want to move this r to the top and then the ke squared here to the bottom. So let's do that, dividing then both sides by ke squared as well. And here we go, the Bohr's radius over here. And what we can do now is for some n integer, we can look at what are the radii, which is some number times n squared. So we just have to show whatever is not n is 0.5 times 10 to the power negative 10. So essentially, this is equal, the one that I have boxed should give us that radius value. So first of all, there's Planck's constant. I'm not going to have space to show all the units, so we have 4 pi squared, which is just straight up whatever that's going to be. M over here is going to be the mass of our electron, since that is what is orbiting, and we also have the K value, which is 8.99 times 10 to the power of 9, and as well as the charge of an electron. And don't forget to square this charge of the electron. And putting all this in our calculator, we're gonna get 5.3 ... times 10 to the power of negative 11 n squared meters so far, okay? And this is very close to 0.5 times 10 to the power of negative 10 n squared meters, okay? So, and keep in mind that these values that we use are from our data table, and that the actual constants themselves have more significant figures, so they're more precise than this one. So this is roughly what it is. So if we take say n equals 1, n equals 2, notice that the Bohr's radius will have specific locations where it will be, and it also scales up the further away you go, so very interesting there. Anyhow, I'm going to stop the video there for this part. In the next part of the videos, we are going to use Bohr's radius to help us find the total energy and how they are discrete as well. So, thank you for watching. Good luck. Vemma Physics signing out.